In 2023, the most powerful telescope humanity has ever built looked at the universe and effectively admitted, "I don't know why it works this way." That is not a tabloid headline. That is the precise meaning of what happened when James Webb confirmed data that dismantles the central pillar of modern cosmology. Welcome to the archives. Enter halls where not merely documents gather dust, but the reverberations of scientific revolutions buried under the weight of accepted paradigms. You were trained to imagine cosmology as a tidy story that runs from the Big Bang to today, a completed structure needing only a few pictures hung on its walls. That is false. Modern cosmology is not a finished edifice. It is the ruins of a grand cathedral whose foundation has split. In 2019, a Nobel Prize laureate rose from the audience at one of the world's most prestigious physics conferences and interrupted a presentation with 9 words. "Don't call it a tension, call it a crisis." The room went silent. Here, in these archives, we will not repeat what you already know. We will speak of what scientists murmur in conference corridors, data hidden in footnotes, numbers that will not come out right. If by the end of this video you write in the comments which fact unsettled you most, we open the next archive. 30 facts, each one another strike against the granite wall of the standard cosmological model. And after the last one, you will never look at the night sky quite the same way. Fact number 1. The number that broke cosmology. For decades, this quantity acted like a cosmic metronome, keeping time for everything that exists. The Hubble constant. It did more than state how fast galaxies recede from one another. It measured the fabric of space and time itself, its expansion. Scientists debated its exact value, but they all assumed it was a single number. Different measurement methods might yield slightly different results because of uncertainties, but ultimately they should converge. That is how physics proceeds. It was an axiom printed in every astronomy textbook. Imagine a hall full of engineers trying to measure a train's speed. Some read the speedometer in the driver's cab. Others stand on the platform and time how fast the cars rush by. Their results can differ a little due to measurement errors, but broadly they ought to agree. In cosmology, those engineers were 2 great teams. The first, armed with telescopes like Hubble, surveyed the nearby universe. They measured light from pulsating stars and exploding supernovae to build a distance ladder and directly determine the galaxy's recession rate. Their speedometer read about 73 kilometers per second per megaparsec. That number felt solid, calibrated, and supported by decades of observations. The second team looked the other way, into the past. They studied the cosmic microwave background, the echo of the Big Bang. Light aged nearly 14 billion years. Using highly sophisticated models, they calculated what today's expansion rate should be if the universe began exactly as they observed it in its infancy. Their answer, obtained with staggering precision thanks to the Planck satellite, was different. 67 kilometers per second per megaparsec. At first, everyone dismissed it as an error. "Check your data," they told each other. They checked, again and again. Years went by. Instruments gained precision, and the discrepancy did not diminish. It became statistically undeniable. This was no longer a measurement glitch. It was a deep contradiction. The universe, as we observe it nearby, is expanding more quickly than the theory extrapolated from its past predicts. It was as if the platform engineers kept reading one figure, while the train driver insisted on a completely different one, and both were certain their gauges were correct. That leaves 2 possibilities. Either somebody is fundamentally mistaken in their measurements, or the train moving from the past into the present has somehow accelerated. This is not a fleeting statistical quirk. It is a crack running through the very foundation of our cosmological framework. And that crack grows wider with each passing year. Fact number 2. The witness who was supposed to settle everything only exacerbated the case. Hope circulated through the scientific community. Its name was the Space Telescope James Webb. Its enormous golden mirror, unmatched sharpness and sensitivity, were expected to serve as the final judge in the dispute over the Hubble constant. Many astrophysicists, especially those who trusted the early universe model, quietly wished that James Webb would find an error in the Hubble measurements. Perhaps, they reasoned, the older telescope simply could not resolve distant stars properly, its view blurred by cosmic dust or by crowded starfields. With its infrared sight able to penetrate dusty veils, James Webb was meant to be a newly calibrated witness brought into the courtroom to reconcile two veteran eyewitnesses. Tension filled the air. The team of Adama Risa, leading proponents of the fast expansion measurement, aimed James Webb at the same targets as Hubble to perform a cross-check. The world of cosmology waited. If James Webb reported a value near 67, it would clear the standard model. If it confirmed 73, the crisis would be unmistakable. Then the data arrived. The images were astonishingly crisp. Stars that looked like single smudges in Hubble's frames were resolved by James Webb into separate points of light. The systematic errors skeptics had hoped for were ruled out. The verdict was delivered. James Webb did not merely back up Hubble, it strengthened those findings. The number remained roughly 73. The hope for a simple observational mistake vanished. Humanity's most powerful instrument looked at the universe and said, "Yes, it really is expanding too fast, and I do not know why." It was a staggering blow. The witness that was expected to exonerate the defendant, the standard cosmological model, instead testified against it. The tension stopped being just a discrepancy. It became an established fact, confirmed by our best tool. Scientists were left not to chase errors in the data, but to search for the flaw in the theory itself. And that made the task far more terrifying, because the old, familiar map of the universe that everyone relied on proved to be inaccurate, and no one possessed a new map. Fact number 3. The ghost of the first error, or how the universe turned out younger than its rocks. We are dealing with the current crisis, a discrepancy of a few percent that confounds scientists. But if we probe deeper into the record, we discover that the conflict over this number was ill-fated from the outset. The saga of Hubble's constant is a history of monumental blunders that render today's problems trivial by comparison. When Edwin Hubble in 1929 first published his findings, he did not merely propose an expanding universe, he attached a numerical value to it. And that figure was grotesquely incorrect. By his reckoning, the expansion rate was about 500 kilometers per second per megaparsec, nearly 10 times larger than the value we measure today. This was no small error. The consequence was absurd. If the universe expanded that fast, its age implied by that constant would be only about 2 billion years. That would not have seemed alarming except for one persistent fact. Geologists already knew the Earth was several billion years old. It implied our planet, its rocks, its oceans, were older than the universe that held them. The child appeared older than the parent. This was more than a paradox. It was a cosmological absurdity that threatened the Big Bang concept itself. For decades, astronomers endured this humiliating contradiction. They suspected a colossal mistake hid somewhere in their calculations, but could not find it. It was the skeleton in the closet of a fledgling cosmology. Only years later, with improved telescopes and a deeper understanding of stellar behavior, astronomer Walter Baade realized that Hubble had mistaken two different types of pulsating stars, Cepheid variables, which produced a catastrophic underestimation of distances. The value of the constant plummeted, the age of the universe increased, and the paradox was settled. Yet the ghost of that initial error never disappeared. It served to warn each new generation of astronomers that their trust in cosmic measurements might rest on unstable ground. Today's quarrel of 67 versus 73 looks like a refined academic dispute compared with that primordial sin of cosmology. Still, it carries the same ominous echo. What if we are mistaken again? What if within our most trusted techniques, in our standard candles, a fundamental flaw lurks that we do not yet perceive, and in 50 years our descendants will regard our debates with the same condescension with which we view Hubble's original absurd figure? Fact number 4. The ladder to the sky, built on fog. To determine the universe's expansion rate, you need two things. How fast a galaxy is receding from us, that is relatively straightforward to deduce from its redshift, and how distant it is, and that is an extraordinarily challenging endeavor. You cannot simply stretch a tape measure to the Andromeda Nebula. To address that problem, astronomers devised one of the most elegant and at the same time most misleading devices in science, the cosmic distance ladder. The concept is straightforward and brilliant. You start with what can be measured directly, distances inside our solar system via parallax. That is the first, most dependable rung of the ladder. Next, you use that information to calibrate the luminosity of nearby stars, for example Cepheids, within our galaxy. Finding the same Cepheids in adjacent galaxies allows you to calculate their distances. That is the second rung. Spotting a Type 1a supernova in one of those galaxies lets you set its peak brightness. That is the third, yet higher rung, enabling observations out to billions of light-years. The SH0ES team, led by Nobel laureate Adam Rees, has refined this approach to near perfection. Their ladder is a study in precision, with each rung meticulously tuned and verified. Each step amplifies accuracy, and it also amplifies possible error. That is both the method's greatest advantage and its greatest vulnerability. Picture a tower built from blocks. If the first block tilts by only 1 millimeter, the second will lean more, and the 100th might even topple. The same applies to the distance ladder. A minute, unrecognized systematic error on the first rung, in the calibration of nearby stars, will become a large offset on the final rung when we measure the most distant supernovae. Critics emphasize precisely this worry. You are erecting a ladder into the sky, but its base stands in the mist. You cannot be 100% certain about every calibration. Maybe Cepheids and other galaxies do not behave exactly like ours. Maybe their light is dimmed by intergalactic dust we have not corrected for. Maybe the supernovae themselves are not as standard as we hope. The Rees team maintains they have considered every imaginable source of error, and their result, 73, is rock solid. Yet skepticism persists. This grand structure that has enabled us to measure the universe is itself the focus of the sharpest debate. And the higher the ladder rises, the more unsettling the idea that a single flaw at its base could topple the whole edifice. Fact number 5. The cosmic metronome that lost its beat. At the core of the distance ladder, on its most crucial rung, sits an extraordinary class of stars, Cepheids. These stars are a boon to astronomers. They pulsate, rhythmically brightening and dimming, and most importantly, their pulsation period is directly tied to their true intrinsic luminosity. Henrietta Leavitt's discovery of this relation in the early 20th century was transformative. It was like finding that every 100-watt light bulb on Earth has a distinctive flicker. Spotting that flicker, you could declare with certainty, that is a 100-watt bulb. By knowing their intrinsic brightness and measuring how faint they look from our vantage point, one could unfailingly determine their distance. Cepheids thus became the cosmic measuring stick, the standard candles that lit the path to other galaxies. They form the foundation upon which the entire modern cosmic distance ladder is built. For decades they were treated as reliably as Swiss watches. Their pulsation seemed like an immutable law of nature. Astronomers assembled catalogs, refined the period luminosity relation, and it appeared the tool had been perfected. But it was precisely here, in this apparently most trustworthy link, that uncertainties began to appear. Do we truly grasp them so well? What if their pulsation depends on the star's chemical composition? Cepheids in our galaxy, enriched in heavy elements, might shine differently from their counterparts in younger, cleaner galaxies. What if their light is modified by unseen dust that envelops them more densely than assumed? The James Webb Telescope was assigned to resolve these arguments. It examined the centers of distant galaxies and identified Cepheids with unprecedented clarity, separating their light from that of nearby stars, and it revealed that Hubble's earlier measurements were surprisingly accurate. But that did not calm the critics. It simply shifted their focus. Now debates concern subtler issues, the calibration of the Cepheids themselves, and whether we are measuring distances to the nearest of them in the Milky Way correctly. The main measuring instrument has become the principal subject of contention. The cosmic metronome that was intended to set a single tempo for the whole universe suddenly began to tick at different rates in different regions. And now no one can declare with certainty which of its beats is the authentic one. Fact number 6. The explosion that was supposed to be identical for all if Cepheids are the 100-watt bulbs of the universe, then Type 1a supernovae are its floodlights, able to outshine an entire galaxy. These extraordinary events occur when a white dwarf, the dense remnant of a dead star roughly the size of Earth, accretes material from a companion star. When its mass reaches the critical Chandrasekhar limit, about 1.4 times the mass of the Sun, it erupts in a thermonuclear catastrophe. Because the mass at the moment of detonation is always approximately the same, it was assumed the peak brightness of the explosion would likewise be uniform. That made them ideal, standard candles for gauging the largest distances in the universe, across billions of light-years. Observations of these supernovae in 1998 led to the startling discovery of the accelerating expansion of the universe and earned the discoverers a Nobel Prize. Their presumed uniformity seemed the golden key to cosmology. All models and calculations rested on the assumption that a Type 1a explosion in one galaxy would appear exactly the same as one in another, at the far side of the observable cosmos. But the more intensely researchers probed these blasts, the subtler features they found. It became clear that their uniformity was not perfect. The hue of an explosion's light can vary a bit. The light curve, how fast a supernova climbs to its maximum brightness and how rapidly it dims afterward, differs as well. Astronomers learned to correct for and standardize those variations to place the explosions on a common scale. Yet, that is like trying to make garments from different tailors fit the same body. You can take them in or let them out, but they will never drape identically. It turned out a supernova's luminosity can be influenced by the age and chemical composition of its host galaxy. Explosions in youthful galaxies, still rich in gas and dust, can on average be slightly brighter or slightly fainter than those that occur in old, dead elliptical galaxies. Each such finding, each incremental refinement, nudges the calibration of the cosmic distance ladder by tiny amounts. And those minute shifts, compounded over vast distances, might help explain why the value derived from supernovae persistently disagrees with the figure inferred from the cosmic microwave background. The mighty cosmic beacon we assumed shone with uniform power in every direction proved to be a more intricate instrument, and now we are not sure we are interpreting its manual correctly. Fact number 7. The woman who built 3 bridges across a chasm, and each led to a different place. In a climate where the Hubble constant dispute had cleaved cosmologists into 2 irreconcilable camps, Rees's team favoring 73 and the Planck team favoring 67, a third influence appeared. Her name was Wendy Friedman, a storied astronomer who for decades had been among the principal figures measuring the universe's expansion rate. She suspected the problem might stem from too heavy a dependence on a single technique, Cepheids. If they were introducing an unseen bias, an independent pathway was necessary. She undertook to construct her own distance ladder using different stars. It was a daring and intensely painstaking effort, an attempt to blaze a new trail through unfamiliar ground. Rather than follow the long-established Cepheid route, Friedman's group concentrated on red giants, ancient, stable stars that at a particular stage in their evolution attain a consistent peak brightness before they begin to fade. This approach, known as the tip of the red giant branch, TRGB, offered benefits. Such stars reside in quieter, sparser outskirts of galaxies, where there is less dust and fewer complicating factors than in the busy central regions that host Cepheids. Everyone awaited her verdict. What value would she report? Her result was meant to be the decisive voice in the controversy, and after many years of work, her team published a value. The number was about 69 8/10, right in the middle. It matched neither of the 2 opposing figures. It did not settle the crisis, but introduced a third, puzzling element to it. Yet Wendy Friedman did not stop. She chose to push further, trying herself 2 more independent approaches, one using surface brightness fluctuations in elliptical galaxies, and another exploiting JAGB stars, a particular group of carbon stars. She constructed not one but three separate bridges spanning the gulf between the nearby and the distant universe. Each bridge ended slightly differently. Three distinct techniques produced three distinct results. None of them matched exactly either the Reese team's outcome or the prediction of the standard model. It was astonishing. Wendy Friedman's saga shows how a quest for a single right answer yielded even greater uncertainty. It hinted that the issue might run deeper than a quarrel between two research groups. Perhaps the universe is not offering a simple verdict because there are not one but several fundamental mistakes hidden in our methods and in our knowledge of stars. Fact number 8. Quiet stars on the outskirts that also could not agree. The discussion about the expansion rate has long centered on the bright, attention-grabbing stars, pulsating Cepheids, and exploding supernovae. They were the headline performers on the cosmological stage, but lurking in their shadows were other, humbler, and possibly more trustworthy witnesses. These are red giants and a specific class called JAGB, J-region asymptotic giant branch, stars. Their chief benefit is their location. Unlike young, hot Cepheids which gather in noisy, dusty, and crowded spiral arms, these older stars dwell in the quiet, tranquil outskirts, the galactic halo. There is less dust there to distort their light, and fewer nearby stars to contaminate measurements. They seemed ideal, impartial judges. The red giant method, TRGB, which Wendy Friedman championed, appeared like a salvation, elegant and grounded in physics. When a red giant's core ignites helium, its luminosity reaches a certain, well-predicted peak. By measuring that peak, one can derive distance. This approach looked cleaner, simpler, and more dependable than the tangled Cepheid story. Yet, when different research teams began to apply it to different datasets, disagreements surfaced. One group, using Hubble telescope data, obtained one value of the constant. Another, studying the same stars but with a different image processing technique, found a slightly different value. JAGB stars, the other alternative Friedman proposed, did not bring decisive clarity either. These carbon stars show very stable brightness in specific infrared bands, making them excellent standard candles, but they too require calibration and introduce their own uncertainties. In the end, the quiet stars on the outskirts, on which so much hope had been placed, failed to reconcile the opposing camps. They only confirmed that the problem is real and difficult. They failed to produce a single value for the expansion rate. Even when questioned in a quieter setting, their remarks would not fuse into a single coherent account. It was like interviewing witnesses from a small village who, unlike the busy city folk, ought to have seen everything clearly and distinctly. Yet their descriptions of what transpired diverged in the particulars. That made the detective cosmologist stop and reflect. Perhaps the fault lies not with the witnesses, but with the event they witnessed? Fact number 9. Echo of creation that predicts another world. Set aside for a moment the telescopes aimed at nearby galaxies. Turn away from the commotion of stars, their births and deaths. Let us examine the oldest light in the universe. This is the cosmic microwave background, or relic radiation. It is not starlight. It is the afterglow of the Big Bang, cooled over almost 14 billion years to a temperature only 2 7/10 degrees above absolute zero. This radiation reaches us from every direction on the sky. It bears the imprint of the universe as it was just 380,000 years after its birth. It is a snapshot of the infant universe. By analyzing this snapshot, cosmologists can do something remarkable. They can construct a model that specifies what the early universe contained: so much dark matter, so much ordinary matter, so much dark energy, and the laws by which it evolved. This model, called lambda CDM, or the Standard Cosmological Model, is extraordinarily successful. With striking precision, it predicts how tiny density fluctuations in the early universe, visible on the relic map, grew into the vast large-scale structure we observe today: galaxies, clusters, and voids. And that same model, anchored in data about the universe's infancy, makes a stringent prediction about how fast the universe should be expanding now. It takes the initial conditions and runs the history forward for 14 billion years. The answer it produces is unambiguous: about 67 kilometers per second per megaparsec. This is not an empirical measurement. It is a prediction emerging from the most successful and tested theory we have. and it does not agree with direct measurements in the contemporary universe, which give 73 kilometers per second per megaparsec. Here lies the deepest root of the crisis. This is not merely a quarrel between two different measurement techniques. It is a clash between past and present, between a prediction based on our most fundamental understanding of cosmic physics and a direct observation of what is happening right under our noses. The echo of creation tells one tale, while the stars we see today tell another. Either we are mishearing the echo, or we are misreading the stars, or, and this is the most disquieting possibility, the story the universe tells contains a chapter we do not know, some physical process that occurred between its infancy and maturity and altered the tempo of its life. Fact number 10. A word spoken aloud at the top of the world. Scientific debates can drag on for years, wrapped in deferential phrasing in papers and presentations. Researchers favor cautious expressions, divergence, discrepancy, tension. Those terms let them preserve dignity and leave room to revise their position. After all, it might simply turn out to be an error that will be exposed. The term crisis is kept for last, when all hope for a straightforward remedy has evaporated, and that term was pronounced. It was not murmured in hallways, but declared at one of the most prestigious scientific gatherings by one of the most respected physicists in the world. This took place in 2019 at a conference at the Kavli Institute for Theoretical Physics in Santa Barbara. On stage was Adam Rees, head of the SH0ES team, a figure whose name is now linked with the fast value of the Hubble constant. He was once more laying out his measurements, insisting the discrepancy was genuine. After his presentation, David Gross rose from the audience, a Nobel Prize laureate in physics and a foundational figure in modern theoretical physics. His remark was aimed at Rees, yet everyone heard it. He said, "Don't call it attention and don't call it a problem. Call it a crisis." It marked a watershed. It was more than a recognition of how serious the matter was. It was an exhortation to stop sheltering behind evasive wording and confront the reality. The word Gross used carried tremendous authority. It indicated that the issue had progressed beyond a quarrel between two observational camps and had reached the realm of fundamental physics. It was a summons to theorists. Guys, your model is broken. Find a new solution. From that instant, everything shifted. Articles titled "Crisis in Cosmology" began to appear with greater frequency. Young physicists who had previously hesitated to tackle the problem, fearing it might amount to nothing, now rushed toward it like prospectors to a rich vein. After all, a crisis in science is not only the demise of an old theory, it is the greatest chance to construct a new one. That instant at the conference resembled a movie scene, in which an old, wise general tells a young lieutenant to stop referring to the approaching force as a small enemy detachment and admit it is a full-scale war. And from that day, the battle for a new cosmology commenced in earnest. Its outcome remains unresolved. Fact number 11. Impossible galaxies in the cradle of time. While some astronomers were still squabbling over the expansion rate, the James Webb Space Telescope was preparing an even more astonishing revelation. It was built to look into the cosmic dark ages, the epoch of the first stars and galaxies. The standard model of cosmology made a clear prediction about what should be seen there. The early universe was expected to resemble a nursery. Galaxies in it were anticipated to be small, chaotic, and only beginning to assemble from primordial gas. To become giants like our Milky Way, they would require billions of years of steady growth, mergers, and accretions. To observe a large, well-formed galaxy at that epoch would be as absurd as finding a grown, bearded man in a maternity ward. And yet Webb trained its gaze into the deepest wells of time, at light that reached us more than 13 billion years ago. There, it found exactly that, the impossible. It uncovered several candidates for massive, fully formed galaxies that already existed just 500 to 700 million years after the Big Bang. They were not merely large for their era, they were monstrously huge. Some of them, by stellar mass, rivaled the present Milky Way. They appeared calm, disk-like, showing signs of ordered structure. By the standard model, they should not be there. There simply had not been enough time for them to grow. Dark matter, thought to provide the gravitational scaffolding for galaxy buildup, could not have gathered into such massive clumps so quickly. Gas could not have cooled and converted into so many stars in that interval. This finding, dubbed the problem of early massive galaxies, opened a second front in the assault on the Standard Model. If the Hubble tension was a fracture in its dynamics, this was a fracture in its structural foundation. It is like archaeologists unearthing a perfectly assembled smartphone amid stone axes. This is not merely an oddity. It is a discovery that forces a wholesale reconsideration of the timeline. And cosmologists now face two unsettling questions: not only why the universe is expanding in the wrong way, but why it assembled complex structures far faster than we ever imagined. Fact number 12. Star factories operating at 100% efficiency. The discovery of these impossible early galaxies was only the beginning. The issue was not just where the mass came from, but how it was turned into stars so rapidly. Star formation is not a very efficient process. In modern galaxies like ours, only about 10% of the cold gas ultimately becomes stars. The rest is either expelled by stellar winds and supernovae, or remains in the interstellar medium. It is like a sawmill that converts only 10% of delivered logs into boards, the remainder ending up as sawdust and waste. Mike Bowman-Colchin, a theorist at the University of Texas, decided to estimate the efficiency at which these early galactic monsters would have to operate to reach their masses so quickly. He took the 6 most massive and earliest galaxies discovered by Webb and ran the numbers. The result was shocking. To produce that many stars in such a short time, those galaxies would have had to turn nearly all their available gas into stars. Their star formation efficiency would have to be close to 100%. This is not just a zero-waste sawmill, it is a magical factory that from one log makes 10 boards. In the real universe, with its chaotic processes, stellar feedback and turbulence, such a value is impossible. That would upend everything we understand about the physics of star formation. It pointed to one of 3 possibilities. Either our core theories of how stars form, tested on thousands of galaxies, are fundamentally wrong, or the early universe followed some different, unknown laws or conditions that allowed gas to collapse into stars with unimaginable efficiency. Or, we simply measured the masses of those galaxies incorrectly. That last idea became a lifeline for many astrophysicists eager to save the Standard Model. What if those galaxies are not as massive as they appear? What if some effect is making them look brighter and larger than they really are? And before long, Webb itself offered a clue that both resolved part of the puzzle and introduced a new one. Fact number 13. Masquerade of the small red dots. Among the strange objects Webb uncovered in the early universe, one mysterious population stood out. They were extremely compact and, based on their red colors, seemed very massive and dominated by old stars. These comprised a sizable fraction of the so-called impossible galaxies. Yet something did not fit. Their light was too intense for such tiny sizes. Astronomers then proposed a hypothesis that turned the situation upside down. What if we are not observing light from billions of stars at all? What if the emission originates in the very centers of these systems, where a far more luminous source is concealed? What if it is the glow of actively growing supermassive black holes? When a black hole voraciously accretes surrounding gas and dust, an accretion disk forms. Material in that disk is heated to millions of degrees and can shine so brightly that it outshines all the stars in its host galaxy. That object is called an active galactic nucleus, or quasar. Normally, quasars emit across a broad spectrum, including X-rays, but if the quasar is enshrouded in a dense cocoon of dust, that dust will absorb the high-energy radiation and re-emit it as infrared light, giving the source a reddish hue. The proposal was bold. The small red dots are not enormous galaxies, but much smaller systems hiding the light of their buried quasars. An actively feeding black hole can blaze like billions of stars, deceiving us and inflating a galaxy's apparent mass. When astronomers carried out follow-up observations to test this idea, they found supporting signs. Many of these objects displayed characteristics typical of active galactic nuclei. It was a relief for the Standard Model. Some of the impossible galaxies turned out to be a trick, an optical illusion crafted by hungry black holes. The problem became less severe, but it did not vanish. It simply changed shape. But if these really are quasars, that raises a new, equally troubling question. How did supermassive black holes grow so rapidly in such an early universe to shine so brilliantly? The puzzle shifted its form but not its essence. The early cosmos was producing colossal objects, whether stellar conglomerates or black holes, at a terrifying, inexplicable pace. Fact number 14. The ghost that remained after the ball. The masquerade ended. Some of the impossible galaxies that had been posing as quasars took off their masks. Astrophysicists exhaled with relief. The standard model appeared intact. Researchers went back through their catalogs, carefully distinguishing genuinely massive galaxies from their imposters. Once the small red dots were excluded from the sample, the confirmed galaxies matched the theory's expectations more closely. The most conspicuous contradictions, the monsters that seemed to break the laws of physics, vanished. Yet when the dust settled and the final count was made, an intriguing residue persisted. The monstrously massive galaxies that would have required 100% star formation efficiency were gone. Still, the population of merely very massive galaxies, those perched at the extreme edge of the model's predictions, remained too large. There were about twice as many as the theory forecast. Picture meteorologists declaring that in a city, no one could be taller than 2 meters 10 centimeters because it was statistically impossible. You step outside and spot 6 basketball players at 2 meters 30 centimeters. That is a crisis. Then you learn that 3 of them were on stilts. You unmask them, and the crisis seems to pass. But 3 genuine giants are still on the street, even though, by the forecast, there should be none. The problem had lessened, but not disappeared. The standard model predicts a statistic: how many galaxies of a given mass should exist at a particular epoch. And James Webb's measurements, even after all corrections, displayed an excess at the heavy end of that distribution. The universe was forming massive objects more readily than we had believed. This was no longer a screaming contradiction that would overthrow physics, but a persistent, nagging mismatch. It hinted at something missing in our model. Perhaps dark matter clusters more efficiently than assumed, or gas cools and turns into stars under different rules in the early universe. The ghosts of the impossible galaxies still wandered the corridors of cosmology, reminding us that even after the masquerade was revealed at the ball, there remained guests no one had invited. Fact number 15. The wheel of time that began spinning too early. At the start of 2025, the archives gained another astonishing entry. In data collected by the same indefatigable James Webb, astronomers found evidence that, again, made them question the straightforward timeline of cosmic history. It was a galaxy, given the unofficial name Большое колесо, and it was remarkable. It was not merely large, it was strikingly ordered. This spiral galaxy displayed distinct arms, nearly as mature and graceful as many seen in the present-day universe. And it existed within the first 2 billion years after the Big Bang. That was something the standard model had not anticipated. The reason is that a spiral form signals maturity and serenity. To fashion those elegant, curling arms, a galaxy must endure an extended, comparatively peaceful existence. Its disk needs to rotate smoothly, without violent disruptions, so that gravitational density waves can gather stars and gas into that refined pattern. That requires both time and quiet. Yet the young universe was far from tranquil. It was an age of upheaval. Galaxies were continually colliding and merging. Supernova blasts and fierce radiation from newborn stars hurled gas about, preventing it from settling into a thin, cold disk. It resembled a vast cosmic cauldron, seething and churning. In such circumstances, creating and maintaining a delicate spiral was nearly impossible. It was like trying to draw a flawless circle on the surface of boiling water. Accordingly, cosmologists long believed the earliest galaxies would be formless, clumpy, and irregular. Lovely spirals, like our Mleczny Put, would have to wait until the universe cooled and calmed. Большое колесо overturned that picture. It revealed that at least some regions of the early universe were calm enough to allow galaxies to grow up well ahead of schedule. This finding did not demolish the model wholesale, but it implied the early universe was far more varied and inhomogeneous than we had thought. Amid the roiling turmoil, there were oases of stillness where processes ran swifter, permitting structures to form earlier than their time. Fact number 16. A portrait of youth in two contradictory strokes. The discovery of Bolshoi Kolosso, a mature spiral in a youthful cosmos, was arresting. It sketched an early universe that could be unexpectedly orderly. Yet almost simultaneously, another team, this one from Cambridgeskova Universiteta, presented a wholly different picture. They did not focus on a single exceptional object. Rather, they conducted a broad survey, studying more than 250 early galaxies also observed by Webb. Their goal was to build a representative portrait of a typical resident of that epoch. The portrait they produced looked nothing like the other. Their verdict was unambiguous. The great majority of galaxies in that era behaved exactly as the Standard Model anticipated: chaotic, turbulent, and formless. They resembled not tidy disks, but the debris left by cosmic collisions. They showed no obvious centers or spiral arms. Star formation in them occurred in fits and starts, unevenly, like a fire struggling to catch in wet wood. This was a domain ruled by the disorder of mergers and gravitational instability. And here a delicate paradox emerged. In the same cosmic epoch, within the same slice of time, there existed two completely different kinds of objects. On one hand, a mature, tranquil spiral that seemed to require billions of years of steady growth. On the other, hundreds of youthful, shapeless fragments surviving amid collisions and chaos. It was as though, on the very same playground, you could watch both sprinting, shrieking toddlers and an elderly gray-haired man with lined skin and a knowing gaze sitting in the sandbox. How could that be? It suggests that galaxy evolution did not proceed uniformly or identically everywhere. Conditions in different regions of the early universe must have been dramatically different. Some galaxies grew in quiet backwaters, reaching mature appearances relatively quickly, while neighbors simmered in a turbulent current of cosmic upheavals. The Standard Model, which seeks averaged, universal descriptions, finds it hard to account for such variety. The universe proved once more to be more intricate and multi-layered than our best theories. It sketched its portrait of youth with two brushes at once, laying down strokes of wild chaos alongside lines of refined order across the canvas of time. Fact number 17. Cosmic cigars pointing to a different culprit. In the standard cosmological model, there is a central protagonist, unseen yet driving the narrative. This is cold dark matter, CDM. Cold signifies that its particles move slowly, allowing them to clump easily into gravitational halos that act as seeds for future galaxies. This picture predicts that the smallest halos form first and later merge into larger systems. Consequently, most dark matter halos, and therefore most galaxies, should be approximately spherical or somewhat flattened. Highly elongated, cigar-like forms ought to be exceedingly rare. A team of astronomers led by Alvaro Poe of the University of Arizona set out to test this expectation with the James Webb. They analyzed the shapes of several distant galaxies that existed in the early universe. Their results delivered another setback to the Standard Model. Several of those galaxies proved to be strongly stretched, resembling cosmic cigars. Their morphologies were wholly inconsistent with cold dark matter predictions. Yet the most striking feature was this: the elongated shapes agreed with the forecasts of alternative theories, models of warm and wave dark matter. In those scenarios, dark matter particles either move more rapidly, warm, or behave like waves, wave, preventing them from assembling into small clumps. Instead, they initially form long, stretched filaments, and galaxies arise within those filaments. Thus, these models predict that the earliest galaxies should not be rounded but rather elongated, cigar-shaped. The discovery by Poe's team was the first observational sign to lean so clearly toward alternatives to cold dark matter. It was like finding a fingerprint at a crime scene that implicated a completely different person than all other evidence had suggested. That did not convict the new suspect, but it did force a re-evaluation of the entire case. And it was a perilous clue, because cold dark matter is not merely a peripheral detail of the Standard Model. It is its foundation. Fact number 18. A frame that might be made of ice. Cold dark matter is not merely one component among many in the Standard Model's cosmic recipe. It is neither the decorative topping nor the icing. It is the cake itself, the layers, the foundation, the structural scaffold that holds everything else up. Remove it or alter its characteristics, and the entire cosmological structure starts to tremble. For decades, theorists have constructed their scenarios on the premise that dark matter is cold. That premise was embedded into every simulation code used to model galaxy formation. It determined how quickly structures would grow, what scales they would attain, and how they would be arranged across space. Nearly every modern cosmology prediction, from the cosmic microwave background map to the tally of dwarf satellite galaxies around the Milky Way, implicitly relies on the properties of cold dark matter. And on grand scales, it performed extraordinarily well. The CDM model portrayed the universe with impressive fidelity, yet on small galactic scales, it has long encountered difficulties scientists euphemistically call the small-scale crises. For instance, the model forecast many more dwarf galaxies in our vicinity than we actually see. It also anticipated very dense dark matter peaks in galaxy centers that are not always observed. Those discrepancies were typically blamed on our imperfect understanding of chaotic star formation physics that could smooth out the forecasts. But findings such as elongated galaxies suggest the issue might lie with the dark matter itself. If it is not cold, but, for example, warm, the consequences are profound. The timing of the first galaxy's appearance shifts, which might account for the impossible detections from Webb. Their shapes are altered. Their inner density profiles change. Virtually every galactic scale prediction of cosmology is modified. Changing the nature of dark matter is not a simple parameter tweak. It is admitting that the steel framework on which we have based our understanding of the universe for the last 40 years might actually be made of ice. And now, in the light of new data from Webb, that ice is beginning to crack. It is a daunting prospect because it would force the reconstruction of nearly all of modern astrophysics. But it is also an extraordinarily exciting opportunity, because it could lead to discovering the true nature of 85% of all the matter in the universe. Fact number 19. A force with a name but no face. Let us shift from the territory of visible and dark matter to the realm of the universe's most enigmatic component. It comprises 68% of the cosmos. It is unseen, untouchable, and its essence is the greatest puzzle in the history of physics. Its name is dark energy. We know only one thing about it. It drives the accelerated expansion of the universe. Its discovery in 1998 astonished cosmology and earned a Nobel Prize. Before that, people assumed the universe's expansion would slow down under gravity, like a thrown stone that loses speed gradually. Instead, it turned out the stone has an unseen rocket motor that grows more powerful over time. This influence has a name and a mathematical place in Einstein's equations, the cosmological constant. It slots neatly into the standard lambda-CDM model. Lambda is the symbol for the cosmological constant. Yet there is no physical explanation for it. Nobody knows what it actually is. The simplest notion is that it is vacuum energy, the intrinsic energy of empty space. Quantum field theory predicts such an energy should be present. The trouble is that, when theorists attempt to calculate its size, they obtain a value that is 120 orders of magnitude larger than astronomers observe, a 1 followed by 120 zeros. This is the largest discrepancy between theory and experiment in the history of science. It is not merely an error, it is a catastrophe. It tells us we are missing something fundamental about gravity or quantum mechanics, or both together. Other proposals are even stranger. Maybe it is a new field filling space, quintessence. Maybe it indicates that the laws of gravity behave differently on the largest scales. We live in a universe two-thirds composed of a substance about which we know nothing except its nickname. Dark energy is not just a missing piece of a puzzle. It is a vast hole in our picture of reality. Until that hole is filled, we cannot claim to understand the world we inhabit. This is the greatest admission of ignorance modern physics has ever made. Fact number 20. The invisible one sought in minds and found in the sky. If dark energy is the deepest mystery, Dark matter is its older, better examined yet equally elusive sister. It makes up about 27% of the universe. Unlike dark energy, which produces a repulsive effect, dark matter behaves like ordinary matter. It attracts. And the evidence for it is overwhelming. All of it is indirect, inferred from its gravitational effects. We observe that stars on the edges of galaxies orbit far too quickly. They would have been flung apart long ago if not for the gravity of an unseen mass holding them together. We see light from distant galaxies distorted as it passes massive clusters, a gravitational lensing effect far stronger than visible matter could cause. We detect its signature on the cosmic microwave background map. Dark matter is the gravitational scaffold that supports all the visible structure of the universe. Its existence is corroborated by dozens of independent observations. It exists. Yet we have no clue what it consists of. For decades, particle physicists have constructed ever more sensitive detectors to catch a dark matter particle. These experiments are stationed deep underground, in former mines and tunnels, to shield them from cosmic rays that can produce false signals. Vast vats of liquid xenon, or arrays of germanium crystals, stand ready for that single instant when a ghostly particle from space strikes an atomic nucleus and generates a faint flash of light or a tiny burst of heat. Billions of dollars have been spent, dozens of experiments have been carried out, and the outcome has always been the same. Zero. Not once. Not a single confirmed detection of a dark matter particle. This produces an odd, almost schizophrenic predicament. Astronomers scan the heavens and see its gravitational fingerprints everywhere with undeniable clarity. Particle physicists peer into their detectors and find nothing. The gulf between astrophysical evidence and the lack of direct detection is becoming increasingly troubling. That drives some researchers to ask a heretical question. Maybe we are searching for the wrong thing? Perhaps it is not a particle at all. Maybe it is a consequence of some modified gravity that acts differently on the largest scales? Most scientists still reject this notion, but the longer the detectors stay silent, the louder the voices of doubt grow. Dark matter is a ghost that haunts our telescopes, yet refuses to appear in our laboratories. Fact number 21. Phantom push in the infancy of the universe. Let us return to the central crisis, the Hubble tension. The dispute between 67 and 73. Theorists, confronted with this persistent discrepancy, began proposing a range of hypotheses to account for it. The majority of these ideas require introducing some form of new physics, something outside the standard model. One of the most popular and elegant proposals is called early dark energy. The concept goes like this. What if the dark energy we observe today, which drives the accelerated expansion, was not the only variety present in the universe? What if during the first few 100,000 years after the Big Bang, there existed another, transient form of dark energy? This putative early dark energy would have behaved like a brief pulse, an extra kick the universe received in its infancy. It would have produced a burst of additional expansion and then, for some reason, rapidly decayed and disappeared, leaving almost no traces. Almost. Its sole enduring effect would be to change the size of the so-called sound horizon, the maximum distance that sound waves could traverse in the primordial plasma before the universe became transparent. And the size of that sound horizon, stamped into the relic radiation, serves as a standard ruler for calibrating cosmological distances and, ultimately, for deriving the predicted value of the Hubble constant. If early dark energy indeed existed, it would have shortened that ruler relative to our usual assumption. And if we recompute everything using this shorter ruler, the predicted Hubble constant would, as if by magic, shift from 67 to 73, matching direct measurements perfectly. Problem solved. It is an elegant, appealing hypothesis. It has only one defect. There is absolutely no evidence that it ever existed. It is purely a theoretical invention designed to plug a hole in the model. It resembles a detective who, finding no clues, invents a suspect who supposedly committed the crime and then immediately disappears. Early dark energy is a specter physicists summon from nothing in a last-ditch effort to save their theory. It could be real. For now, however, it remains one of many shadows wandering the twilight borderlands of known physics. Fact number 22. Echo of a kick heard after 14 billion years. Theoretical physicist Mark Kamienowski of Johns Hopkins University, one of the foremost thinkers in modern cosmology, offered a striking image for early dark energy. He compared it to an unexpected shove given to the infant universe just after its birth. Picture a pendulum swinging with a steady rhythm. That rhythm represents the expansion the standard model predicts. Now imagine that at the very beginning someone gave that pendulum an extra, brief but forceful push. The push stopped almost immediately, yet the pendulum afterwards swung with greater amplitude and a slightly altered period. That nudge transformed its subsequent motion entirely. So it is with early dark energy. This hypothetical burst of extra expansion in the universe's youth would echo 14 billion years later. We do not witness the shove itself, we observe only its consequences, the present universe expanding faster than it would have if that initial kick had never occurred. The metaphor neatly captures how delicately and intricately things are linked in cosmology. A tiny tweak in the physics of the first moments can produce enormous observable effects today. And that is precisely what makes testing such hypotheses so difficult. We search not for the original event, but for its barely perceptible aftershocks. Scientists are actively hunting for such echoes in the subtler features of the cosmic microwave background and in the spatial distribution of galaxies. If early dark energy existed, it should have left additional, weaker imprints, much like ripples on a pond from a thrown stone, that spread in circles and strike the shore. So far, these searches have not yielded results. A model of early dark energy that resolves one problem, the Hubble tension, frequently creates others, worsening the model's fit to other astronomical observations. It is like trying to fix a clock by tightening a single cog. You might correct the motion of the hands, but you will break the calendar. Nevertheless, the idea of a cosmic nudge remains one of the most contested. It illustrates how far theorists are willing to go to explain why the universe's rhythm has faltered. They are ready to rewrite the very first chapter of its history to account for the latest measurements. Fact number 23. The younger brother of the Big Crisis. It appears in journals and is debated at conferences, yet lurking in its shadow is a lesser-known, though no less troubling sibling, S8. While the Hubble tension deals with the universe's dynamics and its expansion rate, S8 pertains to its structure, how clumpy matter is. The S8 parameter measures the degree to which matter, both ordinary and dark, is concentrated on a specific scale. The standard model, anchored by early universe measurements from Planck, provides a very precise forecast for this parameter. It predicts how clustered we should expect the present universe to be. And, much like the Hubble constant, we can also determine this parameter observationally. That is achieved through surveys of weak gravitational lensing. Astronomers photograph millions of distant galaxies and study how their shapes are subtly sheared by the gravity of unseen matter lying between us and those galaxies. Larger distortions indicate a more uneven matter distribution. Here, too, a discrepancy emerges. Direct determinations, performed by several independent projects such as Dark Energy Survey, DES, and Kilodegree Survey, KIDS, repeatedly suggest that the contemporary universe is less clumpy than the standard model predicts. Its matter appears smoother. The difference is not as striking as the Hubble constant case, only a few percent, at the level of 2 to 3 standard deviations. Nevertheless, it persistently remains as new observations accumulate. Adam Rees, the key figure in the Hubble tension saga, aptly labeled S8 the younger brother of the Hubble tension. Both indicate the same reality. Today's universe is somehow different from what it should be, given its past. One problem says the universe is expanding too rapidly. Another, that it is not dense enough. These are two separate hints that could point to a common, as yet unknown perpetrator. New physics that modified the trajectory of cosmic history. Fact number 24. Déjà vu, or how the stars were once older than the universe. Today's crisis in cosmology may seem without precedent, but looking back a mere quarter of a century reveals a strikingly similar episode. In the 1990s, cosmology confronted another, equally profound crisis that at the time seemed intractable. It, too, concerned age and the expansion rate. Observations then, made primarily with the Hubble telescope, indicated a relatively large value of the Hubble constant. The standard cosmological model of that period, which lacked dark energy and contained only matter, both visible and dark, implied for such a value a very young universe, about 9 to 10 billion years. That was disastrous. Astronomers studying star clusters in our own galaxy had already with substantial confidence estimated the ages of the oldest clusters at about 13 to 14 billion years. Once again, as in the era of Hubble's first error, a paradox appeared. The stars seemed older than the universe that contains them. The children were older than their mother. That contradiction struck at the heart of the Big Bang picture. Scientists were frantic. They rechecked everything: measurements of the Hubble constant, models of stellar evolution, age determinations for clusters. No obvious error appeared. It looked as if cosmology had run into a dead end. Then, in 1998, two teams of astronomers studying distant supernovae made a groundbreaking finding. They discovered that the expansion of the universe was not decelerating, as everyone had assumed, but accelerating. That implied expansion had been slower in earlier times. As a result, the universe needed more time to grow to its present size. Adding a new component to the model, dark energy, immediately removed the age problem. The universe's age in the revised model jumped to 13.8 billion years, and the stars at last became younger than their parent. Today, confronted with the current dilemma, many cosmologists feel a sense of déjà vu. Once more, there is a discrepancy between measurements in the nearby and distant universe. Once more, a number refuses to agree. And once more, there is hope that the answer lies in some new physics, an ingredient or law yet to be discovered. The earlier crisis was resolved by the discovery of dark energy. Perhaps the present one signals the coming of something equally fundamental. Fact number 25. The map that was too good to be true. In the annals of science, some instruments achieve legendary status. The Planck telescope of the European Space Agency is one such example. Its mission was to produce the most detailed map of the relic radiation, the echo of the Big Bang. From 2009 through 2013, it scanned the sky with unprecedented precision and sensitivity. When its data were released, they stunned the scientific community. The map that emerged was remarkably precise, clean, almost flawless. With extraordinary finesse, it confirmed the standard cosmological model, lambda CDM. All 6 key parameters of that model were measured to fractions of a percent. It was a triumph. Cosmology appeared to have transformed from a field full of uncertainties into a precise science, where the main constants of the cosmos were known more accurately than some fundamental constants on Earth. Planck handed us the recipe for the universe: 68% dark energy, 27% dark matter, 5% ordinary matter. It exposed the seeds of future galaxies as tiny temperature fluctuations. This was the most beautiful baby photograph of the universe one could imagine. And from that immaculate, crystalline picture, from those triumphant data, came the prediction that would ignite the greatest crisis. It was Planck, with its astonishing accuracy, that predicted the Hubble constant today should be 67.4 kilometers per second per megaparsec. That value was not merely one among many. It was a consequence of the full, magnificent, self-consistent portrait of the early universe. Its mismatch with direct measurements could not be brushed off as a Planck mistake. Quite the opposite, it was precisely the extraordinary accuracy of its data that made the discrepancy statistically indisputable. Planck became both the crowning achievement of the standard model and the source of its deepest trouble. It rendered such a detailed image of the infant universe that we can now assert with confidence: the adult we see today could not have evolved from that infant under the rules we know. The map was too precise. It was so exact that it allowed no latitude or compromise. It delivered an ultimatum. Either everyone measuring the universe now is mistaken, or there is a flaw concealed in this perfect picture of the past that we have yet to uncover. Fact number 26. The geometer who can reshape space. While James Webb looks into the earliest eras, and ground-based observatories fine-tune the present expansion rate, another powerful instrument in orbit could overturn the field. This is the Euclid telescope of the European Space Agency. Named for the father of geometry, the name is deliberate. Its mission is to chart the geometry of the universe on scales no instrument has probed before. For 6 years, Euclid will observe billions of galaxies, covering more than 1/3 of the entire sky. It will do so in two complementary manners. First, it measures weak gravitational lensing, those barely noticeable distortions in the shapes of distant galaxies caused by the gravity of dark matter. That will allow it to produce a three-dimensional map of the dark matter distribution in the universe with unprecedented precision. That will yield the most accurate answer to date about S8, the clumpiness of the universe. Second, Euclid measures the so-called baryon acoustic oscillations. These are a kind of standard ruler, imprinted in the galaxy distribution and left over from sound waves in the early universe. By measuring the apparent size of that ruler at different distances, Euclid will be able to trace the expansion history of the universe over the last 10 billion years. Its data can push the cosmological picture in either direction. If Euclid confirms the low value of S8 indicated by ground-based surveys, that will reinforce the suspicion that something is wrong with the standard model at the level of structure formation. If it shows that the past expansion history diverged from predictions, that could illuminate the nature of dark energy. Its measurements might even help to resolve the Hubble tension by providing new, independent determinations. Euclid is a dark horse in this cosmological race. It does not probe the very earliest past, nor the immediate present. It examines the adolescent age of the universe, the epoch when dark energy began to dominate and acceleration became noticeable. It is precisely in this era that the effects of new physics could make themselves apparent. The first Euclid data have already started to arrive, and in the coming years we may confront new upheavals. This cosmic geometer could reveal that the familiar chart of spacetime requires substantial remapping. Fact number 27. Shadow hunter whose time has not yet come. If Euclid is a geometer, then the forthcoming NASA Nancy Grace Roman Space Telescope is a genuine hunter of shadows. Its chief objective is dark energy, the most enigmatic substance in the universe. It was designed specifically to probe its properties with unprecedented precision. Roman has one major edge over Hubble and even Webb, a vast field of view. In a single exposure, it can cover a region of sky 100 times larger than Hubble. That makes it especially well-suited for extensive surveys. It will use multiple techniques in the pursuit of dark energy. Like Euclid, it will chart the galaxy distribution and measure gravitational lensing. But it will also conduct a large search for distant Type 1a supernovae. If the discovery of dark energy depended on a few dozen supernovae, Roman will discover and study thousands. That will furnish the statistical power that is now missing. With such a huge sample, researchers will be able not only to reaffirm the existence of dark energy, but also to test whether its properties have evolved over time. In the standard model, dark energy is the cosmological constant. Its density does not change as the universe expands. But what if that is not so? What if this is a dynamic field, a quintessence whose strength has varied across cosmic history? The data from Roman will be able to tackle that question. They will give us a detailed movie of the history of accelerated expansion, not merely two stills, then and now. The launch of the NASA Nancy Grace Roman Space Telescope is scheduled for the second half of the 2020s. Its moment has not yet arrived, but cosmologists worldwide await it with bated breath. It may become the instrument that either finally cements the standard model by demonstrating that dark energy is truly a simple constant, or it may ignite a new revolution by showing that its nature is far more complex and intriguing. It might not resolve the current crises, but it will certainly deepen our understanding of the force that determines the fate of our universe. Fact number 28. A view from Earth that almost reached the sky. While space telescopes such as Planck receive acclaim for producing the most precise maps of the cosmic microwave background, equally vital work is being carried out on Earth, in one of the driest and highest locations on the planet. The Atacama Cosmology Telescope, ACT, located in the Chilean Atacama Desert at more than 5,000 meters altitude, has produced the most detailed ground-based map of the cosmic microwave background to date. Operating under such conditions is demanding. The air is thin, and even that tenuous atmosphere of Earth introduces interference. Yet thanks to state-of-the-art instruments and highly advanced data analysis methods, The ACT team produced a map whose resolution in some ways rivals that of space missions. Their observations introduced a new, intriguing shade to the Hubble tension story. By analyzing their own independent measurements of the cosmic microwave background, the ACT team inferred the predicted value of the Hubble constant, and it came out slightly higher than Planck's. Not 73, of course, but not 67 either. Their estimate was about 67 and 9/10, with a modest uncertainty. That was noteworthy. On one side, it did not settle the crisis. The difference between this value and 73 remained substantial and statistically significant. On the other side, it demonstrated that even cosmic microwave background measurements can contain nuances and small systematic differences between experiments. This finding nudged the standard model prediction upward toward the direct determinations, but far from enough to close the gap. It was like two rival camps standing on opposite rims of a canyon, suddenly noticing that one edge had eroded a little and inched a couple of centimeters closer to the other. The canyon did not vanish, but the local geology proved more active than previously believed. The Atacama Cosmology Telescope data are a reminder that science is an ongoing process of refinement. And even in a realm that seems rock solid, such as cosmic microwave background measurements, newer, more precise experiments can still produce surprises and subtly shift the prevailing picture, making the overall puzzle even more complex and intriguing. Fact number 29. 2 cracks in one wall. For a long period, the two principal crises in cosmology, the Hubble tension and the S8 tension, were treated as separate matters. One dealt with the universe's expansion rate, the other with how clumpy matter is. It was possible to design a theoretical model that fixed one issue, but frequently at the expense of worsening the other. For example, some early dark energy proposals that successfully repaired the Hubble constant ended up predicting an even larger discrepancy for S8, amplifying the mismatch with observations. It felt like a game of whack-a-mole. You strike down one popping head, and another springs up right beside it. In recent years, however, a notion has gained ground. What if these are not two distinct problems? What if both tensions, the Hubble one and the S8 one, are real at the same time? What if they are not two independent ailments, but two symptoms of the same, deeper flaw in the standard model? 2 cracks in one wall. This viewpoint changes how solutions are sought. Theorists are no longer aiming for a single patch for one hole, but for new physics capable of both accelerating the universe's expansion, raising h0, and making it less lumpy, lowering S8 simultaneously. That is an extraordinarily demanding requirement. Most modest modifications to the standard model tend to make matters worse. Still, models that aim to resolve both tensions are beginning to emerge. They appeal to unusual scenarios, such as interactions between dark matter and dark energy, or dark matter that decays over time. If both fractures truly stem from the same break, the problem becomes far more serious, but also more promising. It offers us two different angles from which to examine new physics. It is like a detective confronted with two contradictory eyewitness reports. It complicates the investigation, but also supplies extra clues to identify the real culprit. Incoming data from the telescopes Euclid and Roman will be decisive. They will measure both parameters with high precision. If they verify that both tensions are genuine, it will mean we stand on the verge not just of a repair, but of a wholesale revision of our fundamental picture of the cosmos. Fact number 30. The model that does not want to die. After all that has been laid out, after these fractures, crises, and contradictions, one might conclude that the standard cosmological model, lambda CDM, is finished. Yet that is not so, and that is the final, most important, and most challenging fact. The standard model of cosmology has not been falsified. It survives and, perhaps surprisingly, remains robust. True, it has developed cracks that were not present 10 years ago, but we must not forget that the edifice still stands, and it is impressively grand. This model reproduces the cosmic microwave background map with astonishing precision down to the finest features. It correctly predicted the proportions of the light elements, hydrogen and helium, that were produced in the first minutes after the Big Bang. It provides an excellent description of the large-scale structure of the universe, the vast cosmic web of galaxy clusters and voids. On the largest scales, it performs almost flawlessly. Difficulties arise at both extremes. In the very early universe, where Webb finds objects that seem too evolved, and in the very late modern universe, where measurements of the expansion rate and of the matter density disagree with the predictions. It is like a biography that nails childhood and middle age, but completely misreads adolescence and old age. The Standard Model is the greatest intellectual achievement of 20th century cosmology. It united general relativity and particle physics to narrate the history of the universe from the first fraction of a second to the present day. And it will not give up without a fight. Perhaps these so-called crises are not signs of its death, but merely growing pains. Maybe the model does not have to be abandoned, but only augmented. Introduce a new ingredient such as early dark energy, or tweak the properties of existing components like dark matter. We live at a singular moment in history. We inhabit an era when both the quantity and the quality of data are expanding rapidly. We can already perceive cracks in the old map of the cosmos, but the new map has yet to be drawn. And this is the most thrilling time to be a cosmologist. It is precisely out of these crises, out of those moments when nature seems to tell us, "You are wrong," that true science takes shape and extraordinary discoveries emerge. The archives are not closed yet. Their next pages are being written this very moment in front of our eyes.